Hi, this is Sai Podana, founder at Embedded Systems AI LLC. In this video, I'm going to go over design patterns in embedded systems using C language. Embedded systems are fundamentally constrained systems. They're constrained in memory, they're constrained in CPU cycles, they need deterministic timing, they have hardware dependencies, they are interrupt driven, and they need real-time behavior. Design patterns provide reusable engineering structures that help us build maintainable firmware, portable drivers, modular architectures, deterministic systems, and scalable embedded platforms. Even though C is not an object-oriented language, embedded engineers have evolved highly sophisticated architectural techniques using structures, function pointers, callbacks, opaque handles, state machines, queues, and static memory models. These patterns form the foundation of Linux kernel drivers, RTOS frameworks, networking stacks, Wi-Fi firmware, automotive ECUs, storage controllers, DOCSIS systems, and GPU platform firmware. This slide talks about creational patterns. The factory method pattern creates objects without exposing creation logic. Instead of directly instantiating hardware modules everywhere, the system delegates creation to a centralized factory. In embedded systems, this is extremely useful for sensor selection, PHY detection, flash chip detection, board variants, and protocol driver loading. For example, a bootloader may detect whether the board uses a Micron flash or a Samsung flash or an Intel flash and dynamically return the correct driver implementation. This enables hardware portability, cleaner initialization, reduced coupling, and scalable platform support. The next pattern in creational pattern is object pattern. The object pattern brings object-oriented structure into pure C. A structure combines data, state, and behavior. Function pointers emulate methods. This creates encapsulated modules that behave like software objects. Embedded firmware heavily uses this model for UART drivers, network interfaces, device abstractions, protocol handlers, and DMA engines. The third creational pattern is opaque pointer pattern. The public API exposes only a handle while hiding internal implementation details. Users cannot directly manipulate internal state. The benefits include application binary interface stability, safer interfaces, cleaner APIs, modularity, and implementation independence. This pattern dominates in FreeRTOS HAL, Zephyr device models, Linux drivers, NVIDIA firmware SDKs, RTOS middleware. It separates interface from implementation, a critical principle in scalable embedded software. The fourth pattern in creational pattern is the singleton pattern. The singleton pattern ensures that only one instance of a resource exists. This is common for watchdog managers, power controllers, clock managers, system schedulers, and hardware peripherals. Because hardware resources are unique, firmware often uses globally accessible singleton structures. However, embedded engineers use this carefully because excessive global state harms testability, creates race conditions, and complicates concurrency. This slide talks about structural patterns. Callback pattern is the first structural pattern that we're going to discuss. The callback pattern is essential in asynchronous embedded systems. Instead of polling continuously, modules register callback functions. When an event occurs, the firmware invokes the callback. This is the foundation for interrupts, DMA completions, network packet reception, timers, event-driven systems, etc. Callbacks reduce CPU wastage, improve responsiveness, and enable highly modular architectures. The next structural pattern is inheritance-like structures in C. Although C lacks native inheritance, embedded systems simulate inheritance by embedding basic structures. A derived structure begins with a base structure, allowing polymorphic behavior. This enables code reuse, hierarchical drivers, protocol layering, and modular frameworks. The Linux kernel uses this heavily in device models, network stacks, and file system layers. The third structural pattern is virtual API pattern. This is perhaps the most powerful large-scale design pattern in embedded C. Function pointer tables implement polymorphism. Different hardware implementations expose a common API. For example, multiple storage devices may expose read, write, and erase, but internally they might be using completely different hardware logic. This pattern enables hardware abstraction, driver portability, scalable architectures, and runtime flexibility. This is getting used everywhere in kernel, that is Linux kernel, DPDK, Wi-Fi drivers, RTOS device frameworks, and storage controllers, etc. The fourth structural pattern is composition and encapsulation. Composition combines multiple smaller modules into a larger system. Instead of inheritance-heavy designs, embedded firmware prefers composition. For example, a motor control subsystem may combine a PWM module, ADC module, encoder module, safety monitor, and a state machine. Each module remains independent, making the system easier to debug, easier to reuse, and easier to scale. This section discusses embedded essentials, and this could have an overlap with the previously discussed design patterns. HAL abstraction layer separates firmware from hardware specifics. Applications call generic APIs while the HAL translates requests into hardware operations. This enables portability across MCUs, SoCs, ASICs, and FPGA platforms. Without HALs, large embedded systems become impossible to maintain. Next essential component in embedded systems is encapsulation. Encapsulation protects internal state. Modules expose only necessary interfaces. This prevents accidental corruption, uncontrolled dependencies, and tight coupling. Encapsulation improves maintainability, debugging, and scalability. The third essential component in embedded systems is polymorphism via function pointers. Function pointers allow runtime flexibility. The same API can support multiple devices, multiple protocols, multiple hardware generations. This enables firmware reuse across platforms. Static allocation is the fourth essential component in embedded systems. Embedded systems usually prefer static memory allocations. Dynamic memory allocation can introduce fragmentation, non-deterministic latency, memory leaks, and unpredictable failures. Static memory improves reliability, timing determinism, and safety certification. Determinism is central to embedded engineering. The system must guarantee predictable execution behavior. This matters for automotive ECUs, aerospace systems, networking, industrial automation, and medical devices. Worst-case execution time matters more than average performance. Modular architecture is also one of the essential components of embedded systems. Large firmware systems must be modular. Each subsystem should be owning its own interfaces, hiding internal details, and communicating clearly. Modularity allows parallel development, independent testing, and scalable maintenance. This section discusses some common use cases of design patterns. Some of these use cases were briefly touched upon earlier. Now we can look at them in more detail. Device drivers use design patterns to organize device initialization, hardware abstraction, interrupt handling, and driver portability. In RTOS and in real-time OS and task systems, patterns enable event-driven scheduling, synchronization, message queues, and task coordination. As for interrupt handling, callbacks and deferred processing patterns reduce ISR latency. Heavy work moves out of interrupts into worker tasks. In communication stacks, networking firmware uses state machines, producer-consumer queues, protocol layering, and event buses. Bootloaders rely heavily on factory patterns, modular drivers, and abstraction layers. This section discusses some advanced patterns. State machine pattern. The state machine pattern models system behavior through states and transitions. This is fundamentally used in Wi-Fi MAC layers, TCP/IP stacks, Bluetooth protocols, and power management systems. State machines simplify complex protocol behaviors. Observer event bus pattern. This enables publish-subscribe communication. Modules broadcast events without tight coupling, critical for telemetry systems, distributed firmwares, and monitoring networks. Active object pattern combines event queues, private state, and worker execution. This pattern reduces shared state concurrency problem. Producer-consumer pattern decouples data production from consumption, used heavily in DMA pipelines, networking, audio systems, and storage controllers. Ring buffer pattern. Ring buffers provide efficient streaming data transport. Terminate UART drivers, packet processing, logging systems, and audio pipelines. Memory pool pattern. Memory pools provide deterministic allocation without fragmentation, critical for RTOS kernels, packet buffers, and real-time systems. ISR deferred processing. Interrupt handlers must remain short. Deferred processing moves heavy computation into worker threads, tasklets, bottom halves, and RTOS tasks. Lock-free queue pattern. Lock-free queues enable high-performance multi-core communication. Instead of mutexes, they use atomic operations, compare and swap, and memory barriers. This is critical in DPDK, GPU drivers, network systems, multi-core RTOS systems. To sum it up, embedded firmware should keep interfaces small, prefer composition, minimize global state, design for testability, separate interface from implementation, avoid hidden dependencies, optimize deterministically, document ownership and lifetimes. Design patterns in embedded C is not about mimicking object-oriented programming. They exist to solve real engineering problems like determinism, portability, scalability, reliability, maintainability, concurrency, and hardware abstractions. Modern embedded systems, from Linux kernels to Wi-Fi firmware to automotive ECUs to AI accelerators, all rely heavily on these patterns. Mastering these patterns transform firmware from a small device code into a scalable system architecture.